posted. Now, an announcement regarding the final, or a couple of announcements regarding the final. Since classes terminate a week from today, I will arrange for us to have a review session to assist you in final preparation for the final, a week from Friday, next week. It'll be this time slot, since you have this time slot in your schedule. I don't know if I'll be able to get this room. It may be used for another activity. If I don't get this room, then I'll get another room and I'll tell you where. It would be rather pointless if I didn't tell you where. I'll try to make available a couple hours, and I'll run at least in part, if not all, of the review session. Some of my discussion people may wish to participate in this, so I'll give them the opportunity to participate should they so choose. Now, regarding the final itself, as the syllabus tells you, it will be comprehensive, but it'll be comprehensive in a defined fashion. I won't just say everything's fair game, because we've been through a lot. So, regarding questions on material that follows from exams 1, 2, 3, or quizzes 1, 2, 3, I will direct you to the questions and problems on those quizzes and exams by number. You'll know which ones to look at. And in so doing, you can expect to see problems of a comparable nature on the final. Of course, there'll also be new stuff, which is going to be mainly Chapter 24 stuff. And Chapter 23 stuff and Chapter 24 stuff. Now, likely you've noticed the statement that I have in the syllabus regarding determination of course letter grade. Now, in the main, I don't give grades, you give grades. I just keep score. What you earn is what establishes your grade. But regarding the final, since it's comprehensive in nature, I always make available the opportunity for folks to earn a letter grade above and beyond what they would receive if I just treat you by the numbers. The numbers is what you see in the syllabus. I forget what it says right off the bat. I think it says 1,100 points or more for an A, something like that. But if you do particularly well on the final, I'll take that into strong consideration when it comes time for me to sit down and determine letter grades, which then get reported to the registrar's office. So, your aim should be, particularly if you are in need of a grade boost, to do a good job. Do the best you can. And under no circumstances come to me and say, what do I have to make? I'm not interested in talking to budding lawyers. This is not a negotiable issue. Any decisions regarding grade boost lie exclusively and entirely with me. You are not permitted to come and negotiate about this. What are you permitted to do? Make an excellent score on the final. That's what you're permitted to do. And that's what I want you to do. Students have, by this process, in the past, gone up an entire letter grade, from B to A, C to B, what have you. Because they did a very, very good job on the final. Now, be careful. I said very, very good job. Students often wish to interpret this on the basis of improve. Hey, if going into the final you've managed to get 4 questions right on every exam, that's not too good. So let's imagine you get 8 questions right on the final. Hey, you doubled your achievement level, but you're still not passing. And I'm sure you know that. So I don't want to hear any arguments at all, let alone arguments based on the fact that I doubled my achievement level, therefore I should receive a passing mark or whatever. Baloney. Don't do that. Because all you will do is to incur my wrath. We don't want that. If I get upset when I'm in the process of determining these grades for the registrar's office, everybody's grade goes down by 1,000. 2,000? No. Are we understanding each other on this matter? If you wish further explanation, I'll engage in explanation, but not negotiation. There's a big difference. If you wish such, you've got to see me on an individual basis. So we proceed. Let's wrap up chapter 23, which again serves as a marvelous springboard into chapter 24 stuff, the likes of which you began in detail with yesterday's discussion class gathering. So far in chapter 23, at the end, we talked about this very interesting complex compound. Coordination complex, coordination compound, whatever you want to call it. A material formed by the development of coordinate covalent bonds. As carbon monoxide ligands. Ligand is the transition metal chemist's name for a Lewis base. No more, no less. So carbon monoxide ligands, carbon monoxide Lewis bases react with nickel transition metal behaving as a Lewis acid to make this stable adduct. What's unusual about this adduct? It's got a metal in a zero oxidation state. Because, as we have recognized, until now, you've likely seen only metal-containing compounds which are stable, in which the metals are in positive oxidation states. Because the most common chemistry shown by metals is redox reaction, where metals react with nonmetals to make materials which are often ionic in character. Where the nonmetals develop negative oxidation states, like halogens convert to halide ions, while the metals convert to positive oxidation states, like sodium becoming sodium ion. Here, not redox. Coordination chemistry. Point, by coordination chemistry, we can achieve all sorts of marvelous chemical behavior. Very important chemical behavior in many cases. Like the functionality of the chlorophyll molecule. Hemoglobin molecule. Hey, you know about these things, at least in regard to the fact that they're important. Now, we'll also see that the stability of this material is not attributable to the strength of the sigma bonds which are made when each carbon monoxide ligand by use of non-bonding electron density on the carbon end of the molecule makes a sigma bond interaction with nickel. We'll find out that these materials, where the metal is in an unusually low oxidation state, are stabilized not by the ligand to metal sigma bond. Sure, that contributes to stability, but the principal stabilizing factor is pi bonding. You've heard about pi bonding all along. Well, now we're going to talk about pi bonding between metal atoms and ligands. What shall be the origin of this pi bonding? First of all, it will be recognized as role reversal. What the heck's that mean? In making the sigma bond, the ligand supplies a non-bonding pair to an empty valence orbital on the metal. That makes the sigma bond. But in pi bonding, we observe role reversal, or the metal supplies the electrons to make the pi bond, and the ligand supplies empty valence orbitals to accept this pi bond. So the role reversal to which I refer means that in making the pi bonds between the metal and the ligand, the metal behaves as the Lewis base and the ligand behaves as the Lewis acid. Now you know, if we're going to make pi bonds, we cannot use s electrons. They can only make sigma bonds. So what valence electrons, for this specific case, what valence electrons does a nickel atom have that can be used to make pi bonds? D electrons, 3D electrons. How many 3D electrons does nickel in this stuff contain? This is a follow-up of what we said last time. In nickel tetracarbonyl, how many valence D electrons are present in the valence structure of nickel? How many? Do you remember nickel tetracarbonyl is diamagnetic? Do you remember that the bond formation interaction involved drop back of a 4s electron pair in the nickel valence environment for the isolated nickel atom to occupy 3D orbital and convert paramagnetic nickel atom to diamagnetic complex nickel? Remember that? So I ask the question again. In nickel tetracarbonyl, how many valence D electrons does nickel have? 10. So that 9 to be paramagnetic. Remember that? We had the pictures on the board last time. Nickel atom, 3D8 4s2. Well, that's got to be paramagnetic, because you got 2 half-filled d orbitals. But this is diamagnetic. So 3D8 4s2 for nickel converts to 3D10 4s0 for complex nickel. I think this battery just died. Can you hear me all right? Usually folks can. I have a big yap. Or maybe I should say yawp. A big yap for appropriate yawp. How about that? Try this guy for a moment. Now, a consideration which perhaps you heard about in brief yesterday in discussion class. We see that coordinated nickel has an abundance, a full complement of valence d electrons. They can be used for pi bond formation, because it hasn't got any p electrons. So it's going to make pi bonds, it has to use d electrons. Because you can't use s electrons, they won't make pi bonds. What valence orbitals does this thing have which are empty and available for pi bond formation? They have to be p-type orbitals, remember? Because this thing is derived from atoms of period 2, where you only have s and p valence orbitals, and the s orbitals are no good. So there's a directive. See the MO diagram, which is available for your examination in chapter 26 of our notes, the last chapter. Question. In Chemistry 2045, now again, the discussion instructors may have discussed this with you, but it's important, so I don't mind spending some time for brief reconsideration. Did you learn in 2045 that ground state molecular oxygen is paramagnetic? Doubly paramagnetic. It's got two half-filled valence orbitals. Can I represent this by writing a Lewis structure? Now, most chemistry instructors and textbooks will tell you, no, you can't do that. Because they argue that a Lewis picture like this is a violation of the formalisms by which we are to abide when we write Lewis structures. Well, I have a natural reaction to this formalism. My natural reaction is because Lewis structures lie to you. Well, I shouldn't say they lie. That's not fair. They camouflage. They camouflage the valence issue. Because what Lewis structures show you are all the valence electrons. What do they not show you? All the valence orbitals. That's the problem. A formal Lewis structure interpretation of this picture would say, I can't draw this. This is not acceptable. Why not? Because as it stands, each oxygen atom is octet. Right? That's good. This oxygen, one orbital, two orbitals, three orbitals for sigma bond, four orbitals for the pi bond. This oxygen, one orbital non-bonding pair, one orbital sigma bond, one orbital pi bond, one half-filled orbital, and another half-filled orbital. Where the hell did I get this extra orbital? Aha! But now we realize how these Lewis structures camouflage the issue. How many orbitals are really shown by this double bond? 4? 2 orbitals from this atom, 2 orbitals from this atom? Because if you're going to apply Lewis structure formalism, that's the way you're going to count it up. But that's not true. We know that in an orbital, how many electrons can live? 2. Sigma bonding pair, pi bonding pair. So this really represents 2 orbitals, not 4. And I know that an oxygen atom has, all by itself, how many valence orbitals? 4. It's from period 2. So how many orbitals are really shown to be occupied by this picture? 1, 2, 3, 4, 5, 6, 7. There's still another orbital there, isn't there? And that's the part of this picture that Lewis camouflages. 8 orbitals. And we're going to find out that this remaining unoccupied orbital is a pi-type orbital. For carbon monoxide. Well, let's go back and count. Let me slow down a bit. How many orbitals are in fact shown to be occupied by this picture? How many? How many? 5. Oh, I'm pointing here. But you got 1, 2, 3, 4, 5 electron pairs, right? That's 5 occupied orbitals. But how many total orbitals are there? Is this from period 4? A 2? This from period 2? How many orbitals total? 8. Hey, where's the other 3 orbitals? This picture doesn't show you that. But this will. So take a look at this. More on this pi bonding business later. Let's proceed. Argument. By analogy to valence structure of transition metals, 36 krypton can be argued to have how many valence electrons? Well, let's make the analogy to the transition metals. Because what distinguishes and separates the chemistry of transition metals from non-transition metals is that they have a mixed bag of valence electrons. D's and S's. First row, period 4 transition metals, 3D and 4s valence electrons. Second row, 4D, 5s. Third row, 5D, 6s. They all have a mixed bag of valence electrons. Well then, if I'm going to count these electrons as valence, if I proceed, when I get to gallium, how many valence electrons do I have? I get an s2 pair, a singly occupied p orbital, both an energy level number 4,
3,
and a full 3D shell, don't I? Hey, 13. Let's keep counting. 14, 15, 16, 17, so when I get to krypton, 18. Where I'm counting 3D, 4s, and 4p electrons, all as part of its valence structure. That's 18. Now, why do we use this device? Because it helps us to rationalize stability of materials like this which have unusual properties. And it helps us also to predict when these materials can be expected to be stable as opposed to not stable. Let's take a look. This is known. This is stable. This is not known. This is not stable. If we were to consider the possibility of this stuff existing, how many valence electrons would be in the valence environment of nickel? Maybe it will be helpful if we go back and reconstruct the valence orbital energy level diagram for the nickel atom in this tetracarbonyl material, which is stable. First, we recognized that unlike the nickel atom, complex nickel in this stuff is diamagnetic. So the 3D8-4s2 configuration converted to 3D10-4s0. That gave us this. That accounts for the diamagnetic nature of this stuff. And then we said, hey, you got 4 ligands, 4 carbon monoxide Lewis bases coming in to make 4 sigma bonds. Each contributes a non-bonding pair. Well, these have to occupy empty orbitals supplied by nickel, and the lowest energy available empty orbitals after this reconfiguration of valence electron density for the nickel atom is this is empty, this is empty, this is empty, and this is empty. So we'll argue that one of the non-bonding pairs takes occupancy in this orbital and then becomes a bonding pair because it formed a coordinate covalent bond with nickel. These are the electron pairs supplied by the 4 carbon monoxide Lewis-based ligand molecules. 1, 2, 3, 4. And we said, hey, how do we name hybrids? You name them in terms of the orbitals which were used to create. We use 4s and each of the 4 p's. So this is S, P1, P2, P3. SP3. And you've seen this before. SP3 corresponds to tetrahedral geometry. So you expect nickel tetracarbonyl to show an sp3 hybridized nickel atom. Well, you can't observe hybridization, that's just a theory. But you can observe geometry, and that's tetrahedral. And this thing is tetrahedral. So we say, hey, this is pretty good. We explained it. Now then, if we had this stuff, how many valence orbitals, how many valence electrons would be in the valence environment of nickel? 16. Not stable, not observed. If we had this stuff, and this is a typo in the statement of this question, I retyped nickel tetracarbonyl. So if you look in your notes, you should change this to, because what I intended here was a sub 5. You see in the statement of question 66? It should read tricarbonyl and pentacarbonyl. That also doesn't exist. If I had this, I'd have 20 valence electrons in the valence environment of nickel. The only one which is existing is this thing where you've got the 18 valence electrons. So once again, we see an analogy regarding Analogy based on the tendency of atoms to react to achieve what kind of valence electron structure by reacting? Noble gas structure. Now like that of krypton. So with that, we can take a look at question 67. Iron also forms a zero oxidation state carbon monoxide complex, which means the iron itself is in zero oxidation state. What's the value for X? I heard a vote for 5. Any seconds? I'm taking 5. Iron is atomic number 26. It has a total of how many valence electrons for the isolated iron atom? The isolated iron atom, all by itself. How many valence electrons does it have? 8. Well, how many more do I need to get to 18? 10. That means 5 pairs, don't I? That's why X is 5. All right, what about hybridization? Let's take this diagram and now use it for this stuff. Which is also diamag. Here's iron before you make the complex. This is iron before you have bond formation interaction with carbon monoxide. Hey, now the bond formation interaction results in getting all these electrons, which formerly belonged to iron, to pair, and shoves these back into here. So here's what you get. And with carbon monoxide being, with X being 5, 1, 2, 3, 4, 5. What's the label for this hybrid? Is the label for this hybrid sp3d or dsp3? What is it? It's dsp3, because these d orbitals are from what energy level? 3. This label means the d orbitals, like the s and p orbitals, would also be from energy level number 4. You don't have that for this. You have that. But it's the same blend of orbitals, dsp3 as sp3d. The only difference is the energy level from which the d orbitals came to make the hybrid. Because for this hybridization scheme, the d orbitals are lower in energy than the s and p orbitals. They're from energy level number 3. That's why we write d in front. Geometry? You've seen this before. Trigonal bipyramid. All right, trig bipyr. Now what are we going to do in the laboratory to find out if all this fancy storytelling is correct? Well, first we'll observe magnetic character and find out this is diamagnetic, just like nickel tetracarbonyl, whereas the iron by itself is magnetic. You know iron is magnetic. Ferromagnetism, which is the magnetic property shown by a bulk sample of iron, is what you get when all these individual paramagnetic iron atoms put all their magnetic fields in the same direction. You can remove that character because the average sample of iron isn't magnetic. Because although each individual iron atom is paramagnetic, these electrons are pointing in all kinds of different directions, and their magnetic fields cancel each other. But you can take a piece of iron and turn it into a magnet, can't you? You know that. Now you got all these electrons with their magnetic fields in the same direction. That's ferromagnetic. And we also go to the laboratory with a sample of this stuff and observe its structure. And we see it's trigonal bipyramid. So we pat ourselves on the back and say, oh, that's good storytelling. Because the story fits the facts. Now we look at 68. 3 possible complex of cobalt with carbon monoxide. And remember, CO does not equal CO, damn it. Which we told you last time. Which of these do you expect to be stable and why? +1 complex, 0 oxidation state complex, -1 oxidation state complex. Which one's stable? The one with 18 electrons in the valence structure of cobalt. Which one contains 18? How about this? So guess what? Now we got a stable material containing a metal with the metal in a negative oxidation state. More wonderful stuff that you can do with coordination chemistry. And you can't do it with any other kind of chemistry that I know. Here's another one. This is a known stable complex of iron. 3 carbon monoxide molecules and 1 NO plus ligand. A most unusual ligand. Wouldn't you say? Because at the minimum you learned yesterday that ligands are known as such, transition metals, Lewis bases, because they are capable of doing what? Supplying one or more non-bonding pairs which convert to bonding pairs in the bond formation process, right? They're electron pair suppliers. It's not redox. They're not losing the electron pair. They're not transferring it entirely. They're sharing it with the metal atom or ion with which they bond. So in this stuff, you need to realize that the oxidation state of this ligand is +1. For each of these, 0, because they're molecules. So what's the oxidation state of iron in this stuff? What is it? What is it? -2. How about that? So here's a metal in an even lower oxidation state compared to the cobalt situation. Now then, in passing, I made the remark that this is a most unusual ligand. Why so? Isn't this composed of atoms which are of appreciable electronegativity? Isn't this a cation? How effective do you think a cation will be at sharing non-bonding electron density with something else? Good or bad? Coulomb. Good or bad? Good or bad? Bad. Damn thing's plus. Plus it's composed of highly electronegative atoms. Trying to get electron density away from this thing is not easy. So here is assuredly a case where we can argue, and must argue, that the stability of this stuff is attributable to this pi bonding business. How many d electrons does iron have in this? Hey, you should now recognize at a glance that since these complexes which contain the metal in an unusually low oxidation state are going to be krypton structure, that the 3D valence shell for period 4 transition metal atoms will always be full. On it? Anybody got it over there? The 3D valence shell is full. Now, how many of these 3D electrons are formally iron? Well, this one, pardon me, let's get this straight, because what I had there was for this thing. Now I'm going to make the picture for this thing. There. Ten 3D electrons for this thing. For that iron pentacarbonyl, you had 10 electrons in the 3D subshell, but 8 were formally iron. Because one electron pair was contributed to the 3D subshell by one of the carbon monoxide ligands. That's how we got the DsP3 hybridization. All right? So, hey, if I have recognized for something like carbon monoxide that I've got empty p orbitals which can make pi bonds, you think I can make pi bonds with this thing? Isn't this electronically just like carbon monoxide? Do you think this will be a better pi bond former even than carbon monoxide? This is plus. It's pulling on these d electrons. Come on, share them with me. Let's make good strong pi bonds. You betcha. This makes marvelously strong pi bonds as far as metal ligand interactions are concerned. You see, this stuff is fundamentally Coulomb. Iron in a -2 oxidation state with a full complement of 3D electrons, interacting with a ligand that is composed of atoms of substantial electronegativity with a positive charge that has empty orbitals to make pi bonds. I remind you again, take a look at this. Okay? Now then, extending this idea. Can I make stable complexes with the metal in an unusually low oxidation state which show square planar geometry? Now, I make this consideration because square planar geometry is a geometry that's very common to a number of transition metal complexes. But the question we're asking here is for transition metal complexes which are square planar, would I expect them to contain a metal in an unusually low oxidation state? Because if such a complex is stable with the metal in an unusually low oxidation state, how many valence electrons do I expect to count for the complex metal? Krypton. 18. All these things we're talking about, all got these 18 valence electrons in the metal valence environment. Every one of them. Well, let's see if we can get that with square planar. Now, if you haven't seen the orbitals which are hybridized with each other to correspond to square planar geometry, I wrote it over there. DsP2. Okay? So metal electrons would be here, 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 and here. 3D empty. S, P, and P. Can this possibly have 18 valence electrons for the complex metal? No way, because that third energy level 4 P sublevel cannot be filled for DsP2 hybridization. So you're never going to see square planar geometry shown by these complexes which contain the metal in an unusually low oxidation state. Hey, all follows by analogy to this krypton electron configuration. Now then, since we dwelled on this DsP2 hybridization, square planar, if This is my square plane. And this is a picture of the dx squared minus y squared orbital. Then the x-axis and y-axis, respectively, pass right through the hearts of the lobes of this particular orbital. 3dx squared minus y squared. Now we'll do some more of this later. But the question I want to ask is, if I take this to be the xy plane, which of course it must be, x-axis, y-axis, and here's my complex that's square planar, metal here, ligand here, ligand here, ligand here, ligand here, and the 3D orbital used to make the hybrid is x squared minus y squared, given that its orbitals are in the xy plane and have the lobes skewered right through the middle by the x and y axis respectively. Which p orbitals do I use to make this hybrid? Which p orbitals? How are the p orbitals labeled with a geometric reference? You remember px, py, pz? Because you remember a family of p orbitals? Looks like this. And the remaining one is hard to draw, because this is in the plane of the board, this is in the plane of the board, and that one's this way. Lobe sticking out this way and the lobe behind. Now, PZ, PX, PY. Because transition metal chemists, when they play with Cartesian coordinate reference axes, this way is X. But this way, I'm sure until now, this way has always been Y. But transition metal chemists call it Z. Who cares? Which means by default, this way is Y. Okay? So if this be the case, this is X direction, this is Z direction, up and down, which means by default, Y is this way. One lobe pointing at you, the other lobe pointing at me. Which p orbitals are used to make this dsp2 hybrid? Given that the complex lies in the xy plane and the d orbital used is x squared minus y squared, which I already have explained. Which p orbitals? Which ones? P. I want the labels. PX and P what? Z. Because PZ and PX are in the plane of this board. So I'll take these, turn it a little bit, and I'll overlap the PX. Whoop. Damn it. PY. We got to use PY. I got to rotate this so PZ is going this way. In my rush to get through this, I forgot the planar orientation that I cast for the complex. So to make this, if I imagine the complex is in the XY plane, then I use the PX and PY. Let's get that. If I imagine this to be in the PZ plane, the XZ plane, then I'll use PX and PZ. And if I imagine it to be in the ZY plane, then I'll use PY and PZ. Okay? Pardon my mess up of this geometry lesson. But we'll do more on this. We'll get that untangled. Don't worry about that.